Okay, good afternoon, everyone. Today I'll give a lecture about fractional order model nonlinear predictive control using RIOTS 95. My name is Tiebiao, and my instructor is Professor Yang Chun. First, I'll give a basic background of my FISP, and then I'll give some basic ideas of model predictive control using RIOTS 95. And then I'll give a brief introduction about Osloop recursive approximation and Longaberger observer, which can be used to extend the RIOTS MPC to a fractional order plant. Here's the three paper, and in this paper, there has been Dr. Chen has proposed RIOTS 95 MPC for integral order plant, and in these two papers, Dr. Chen proposed general optimal control problem method for fractional order plant, and they use two different approx method. In this paper, Osloop approximation method was used, and in this paper, singular value decomposition based rational approximation was used. And so from here you can see that this is a model, RIOTS model predictive control for fractional order, for integral order. And here are two papers for you can deal with optimal control problem for fractional order. But this is an open loop, not a closed loop. So here we can combine these two ideas to design the RIOTS 95 MPC for fractional order. And first, let me introduce the model predictive control philosophy. Model predictive control was introduced first by an engineering in Shell factory in petrol control. And there are types of model predictive control. One such as dynamic metric control and generalized predictive control and model algorithm control. But behind all this model predictive control algorithm, there are same basic ideas. The idea is that at time t, the controller will solve an optimal problem over a finite horizon over n steps. And the optimal control problem can be described by this. And here is the cost function. And here is the discrete equation to describe the system dynamics. And here are constraints on control input and control system output. And after we solve this optimal control problem, we get the optimal series control output. But we only apply the first control output, U star t. And at time t+1, when we get new measurements, and we will repeat the optimization. So from here you can see that by repeat optimization, we can get nearly feedback control. So actually, in this book is published in 1967. So you can say this, and in this book, Lee and Marx stated that to transfer the open loop control to feedback control, we just can measure the current control process state and then compute very rapidly for open loop control function. And by this way, we can transfer the open loop control to a feedback control. And we can see this is the basic idea that model predictive control that has used. So based on this idea, we can we can transfer RIOTS 95 to model predictive control, close the loop. So let me here give a brief introduction about RIOTS 95. RIOTS here, it means a recursive integration optimal trajectory solver. It can solve kinds of optimal control problems. And we just need to provide several M files to describe the optimal control problem. And then we can just use this command in M file, and we can get the desired control output and the corresponding state and objective function value. Here we need to attention, RIOTS 95 provides three kinds of integration methods, Euler, Ruger-Kutta, and Lossada. And here we need to attention that for integral order, we just use the Euler or Ruger-Kutta. But for fractional order, we need Lossada. It provides higher accuracy method. So here is the problem description, and that RIOTS 95 we can solve that. And here is the objective function. Here, this is denote initial state, and this denote endpoint state, and X is state, and U is control output. So here, and this is describe the system dynamics, and here is the constraints on control output and initial state, and here is the constraints on control output and the state. And from here we can see that this problem RIOTS 95 can solve is similar as the problems that need to be solved in model predictive control. They both have system dynamics equation to describe the control system, and they both have the constraints on system output and control input. So based on the idea I mentioned before, that transfer the open loop control to closed loop control, and the similar optimal control problem, we can combine the RIOTS 95 with model predictive control. And here is the RIOTS model predictive control using RIOTS 95. Here we can say this is the state space equation to describe the system, and this is our RIOTS 95 MPC. And here we can say by using online optimization of optimal problem, we designed this controller. Here we give the example that how RIOTS 95 MPC can control an unstable problem. We can say that this system has a positive 2 root in the positive part of the complex plane. And we can say within 5 seconds it can reach the set point at 1. And this is the control output. Here we place the maxi value 1 at the control output. And here we have make a comparison with MPC toolbox in MATLAB. And this is the example in MPC toolbox in MATLAB. And here is built by MATLAB by RIOTS 95 MPC. And the sample time is 1.1, and this is a predictive horizon, and this is a manipulative horizon. And similarly, we have the predictive horizon, and we have the target value, that means the reference input, and here is also the reference input for MATLAB Toolbox MPC. And here we can see the dotted line is RIOTS MPC, and is MATLAB MPC, and the solid line is RIOTS MPC. And here is the system output. Here we can see RIOTS MPC can get as good as control performance as MPC into MATLAB Toolbox. And here, to use the RIOTS 95 MPC into fractional order plant, we need two other methods. First, we need to slope recursive approximation to transfer the fractional order to integral order. And here is the method. And there has been a software MATLAB Central, which is designed by Dr. Chen. And here is an example that shows how a slope recursive approximation can approach the real fractional order. And here we use two methods to calculate the step response of this fractional plant. And the first method is numerical inverse Laplace transform, and the second method is by a slope recursive approach. Here we can see the results are almost the same. And to use the RIOTS MPC to fractional order, we know we have to get the state variable to use RIOTS to calculate its optimal control output. So we use the Lemberger observer to estimate or to observe the real system state. Here x dot is the real system state, and here this is the observer state, and this is the error. We can see by select the gain metric G property, we can place the eigenvalue of this metric at the negative part of the complex plane. So the observer can be asymptotically stable, and the state get by the observer can approach the real system closely. Here's an example that.
Just have a question about the observer design. What is the measured state, and what are the states that you are trying to estimate?
Here RIOTS 95, the equation to describe the system dynamics is like this. So we have to get the state of this system. Okay. So, but when we transfer the fractional order to integral order, since the integral order is larger than 1, right? So there will be more than one state we need to know. Yeah, we need to know to use RIOTS 95 to solve this problem. Okay. Yes. Yeah. So we use the Lemberger observer to approach this the state that caused by this approach method. So here we can see in the first figure there's no step disturbance, and we cannot distinguish which is the real system and which is the observer state. In the second figure, we add a step disturbance to the output, and we can see that within 5 seconds it can approach the output of the real system. So it works well to to estimate the state of the real system. And here is how we can extend the RIOTS MPC for integral order to fractional order. First, we use the Oslo recursive approximation to transfer the fractional order plant to integral plant. And then we use the Lomberger observer to get the unknown state of the system. And then we use the RIOTS 95 MPC to control this problem. And here is the control schema that how RIOTS 95 MPC with observer to control the system. Here we should pay attention that the order of the observer may be not the same as the real system, because the real order of the system in the world, in practice, we did not know. We just estimate. So I give some examples to show that RIOTS 95 MPC can not only deal with a single input, single output system, but it can also deal with a multi-input, multi-output system. Here is an example that when the state of when the state of the observer is the same as the real system, we can see that the system output reach the desired output. Here the set value is 10, and the control performance is good. And here we can see that the state of get by observe is really the same as the real system. Here is the example that the order of the observer is not the same as the real system. Here we use the real system order is 9, and the order of the observer is 5. Here we can see though the state of the observer and are different from the state of the real system, but we can see that the control output, the system output, it can also reach the desired output. And at 30 seconds we add state disturbance. You can see that it can also reach the desired output as shown. And here I give an example about how RIOTS MPC can deal with a multi-input, multi-output system. And the system can, for example, the system described by this. It has 2 input and 2 output, and the desired output is 10 and 1 for the first and the second output. And here we also give a step disturbance at 30 seconds. And here is the result. From here we can see the first and the second output can reach the desired output. And also we can see that at 30 seconds, when the step disturbance is added into the system, it can recover to the desired output within 3 seconds. And also here we have attention that this control output is as high as 12. So to show the constraints that RIOTS 95 can deal with, we place a control output constraint is 11 and 3 for each control output. Here we can see the control output is within the constraints. And future work. And from the example that has been shown, that we know the RIOTS 95 MPC can deal with unstable system and single input, single output, and multi-input and multi-output system. But we did not deal I will try on large time delay system, and also here we used the Limburger observer to get the state of the real system, but this kind of observer is effective without stock noise. But when there is a stock noise, stock stick noise, there maybe we have to use the common filter, and I will have a try later. And later I'll try to use the test our RIOTS 95 MPC on this kind of TITO platform. That's all. 2 input, 2 output. Thank you very much.
Good timing, and you left 5 minutes, and we can have some discussion. Question?
I have a question. I'm not really sure, but your previous slide you said you used solve room cutoff 2, 4, and 6, right?
Yeah.
And another method is what? I couldn't understand what kind of method is LO.
It is
Adams. So it's a variable step.
Okay. So here you said one using the Jacobian, another one saying without Jacobian. So what kind of method if you don't use without Jacobian?
It is there's a detail in one paper. I can show you that paper. Yeah.
You need to understand the explain. Other questions? Control? People?
Control people.
I'm interested in the LIGO experiment.
My more part is multi-input multi-output, right?
So from this, again, we see that if we do singular SVP, singular decompensation or the condition number, the 0, 2 effects, I guess both of the two outputs should be controlled by the we can discuss afterwards. Let's just quickly see the next slide. That's interesting here. Which is the control.
This is the control.
We can discuss afterwards.
Okay.
All right, here's a question.
Yeah. I know that there is the first step in the observer design of the system is how to check the observability of the system. Did you do that here, and how did you do it?
We can you mean how to select the
Yeah, how to?
Observability question. So why you should observe that is something that is never observable. We don't do that. We check observability first. So this is a string that there's you want to sell. So last question, if you still have one. Okay, there's a comment.
So you use the RIOTS 95. So do you have RIOTS 2013?
That's excellent. That's an excellent question. So
Yeah, we have RIOTS 2013. It will be transferred on Win64 platform. So you can also use on Windows 64 platform. Yeah. And also I will do some friendly interface to RIOTS 95. So it will keep changing.
I think right now